Hey, today we're going to look at a very important series convergence test known as the integral test. Here's the basic idea. Imagine you have a series that you're looking at, sum n equals 1 to infinity of a sub n, and you build yourself a function f of x such that f of n is equal to a sub n for every natural number. In other words, f of 1 gives you the term a sub 1, and f of 2 is equal to a sub 2, and f of 3 is a sub 3, and on like that forever. Then the integral test tells us that if that function is continuous, positive, and decreasing on the interval from 1 to infinity, then the series converges if and only if the improper integral from 1 to infinity of that function converges, meaning if improper integral converges, so does the series. If that improper integral diverges, so does the series. And let's look at why this is true. Here we have a function that is continuous, positive, and decreasing from 1 to infinity. And you may recall estimating the area under the curve using these Riemann sums, this idea of building rectangles underneath the curve. And here I've done that where each rectangle has width 1 and height equal to the function value at the right-hand endpoint. So in other words, the height of that first rectangle is based on whatever f of 2 is equal to is. The height of the second rectangle is f of 3, etc. And it's easy to compute the area of these rectangles. The width is 1, and the height of the first one, for example, is f of 2, and f of 2 is a sub 2. That's how we chose the function f, so that at each of the natural numbers, it would give the terms of the sequence. And so the area of that first rectangle is 1 times a sub 2, or just a sub 2. And similarly, the area of the second rectangle is a sub 3, and then the next one is a sub 4, and the next one is a sub 5, and I haven't drawn in the infinitely many that come after that, but they work similarly. Okay, let's look at the same function again and estimate the area under the curve. Instead of using rectangles with right-hand endpoints, we'll use rectangles with left-hand endpoints. Like so. So here, the height of each rectangle is determined by the function value at the left-hand endpoint. So the height of the first rectangle is f of 1, and the height of the second rectangle is f of 2, etc. Then once again, it's easy to compute the area of these rectangles. The width of each one is 1, and the first one has a height of f of 1, and f of 1 is equal to a sub 1, and so the area of that first rectangle, 1 times a sub 1, or a sub 1. And the area of the second rectangle is a sub 2, etc. And on forever, even though I've only drawn the first 4. And here's the punchline, basically. Both of these infinite sums of rectangles give us estimates of the area under the curve. The exact area under the curve from 1 to infinity is the improper integral, the integral from 1 to infinity of f of x dx. The estimate on the left, using right-hand endpoints, is an underestimate of that area, and that estimate on the left is the sum as n goes from 2 to infinity of a sub n, and the estimate on the right is an overestimate of that area, and that estimate is the sum as n goes from 1 to infinity of a sub n. And so we have that the sum n equals 2 to infinity of a sub n is less than the integral from 1 to infinity of f of x dx, which is less than the sum as n goes from 1 to infinity of a sub n. And the beauty here is that these two series differ only by a single term, and so they either both converge or both diverge. We saw last time that you can discard finitely many terms from a series, and it doesn't change whether or not the series converges. Here we're discarding one term from the series, so both of these two series either diverge or converge. Suppose the integral, the improper integral, diverges. Well, it's smaller than the series on the right. So if that improper integral goes to infinity, then so does the series on the right, the sum n equals 1 to infinity of a sub n, and that's the series that we're talking about. So if the improper integral diverges, so does the series diverge. On the other hand, suppose the improper integral converges to some number. Well, the sum n equals 2 to infinity of a sub n has to then be smaller than that finite number, so it must converge. And if it converges, then so does the sum n equals 1 to infinity of a sub n. And that's the proof of the integral test. Let's look at an example. The harmonic series, which we have already shown through some clever argument that this series diverges. Now we ought to be able to show that it diverges using the integral test. Consider the function f of x equals 1 over x, then that function is positive, decreasing, and continuous from 1 to infinity, and f of 1 gives us the first term, and f of 2 gives us a half, the second term, and f of 3 gives us a third, the third term, etc. And so we can compute this improper integral, the integral from 1 to infinity of 1 over x dx, and whether or not this converges will tell us whether or not the series converges. And the improper integral is defined in terms of this limit, and the integral of 1 over x is of course the natural log of the absolute value of x. And so we get the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. Well, the absolute value of 1 is 1 and the natural log of 1 is 0. And so this reduces to the limit as b approaches infinity of the natural log of the absolute value of b. You don't really need the absolute values because b is approaching infinity, so it's certainly positive. But as b approaches infinity, natural log of b also approaches infinity. And so that tells us that this improper integral diverges, and that tells us by the integral test that this series, the harmonic series, diverges, which we already knew, but now we know it all a second way. Okay, you try this one. Take a moment and see if you can prove that the series sum n equals 1 to infinity of 1 over n squared converges. I'll give you a hint. Use the integral test. Pause the video. When you're ready, start it back up, and we will see it together. You have to consider the function f of x equals 1 over x squared, which is positive, continuous, and decreasing from 1 to infinity, and which gives us the terms 1 over n squared at every natural number n. And so we can look at this improper integral, which is defined in terms of a limit, and is not hard to integrate. You get x to the negative 1 over negative 1, which is negative 1 over x. And when you evaluate it from 1 to b, you get the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Well, as b goes to infinity, negative 1 over b goes to 0. And so simplifying, this improper integral converges to 1. And that tells us that the sum n equals 1 to infinity of 1 over n squared converges. Just to be clear, it does not tell us what it converges to. It certainly does not converge to 1. And so the integral test tells us that the integral converges, but we have no idea what it might converge to. And in general, we will not be able to tell what some integral converges to, with the only exception being the geometric series, and this particular one, which we'll spend, one video or class period on towards the end of the semester. It turns out through some clever trickery, we can figure out what this converges to, but it will not be at all simple or trivial. Okay, that was the integral test. There is, of course, a homework to try on that, so have some fun with that. For the most part, we will use the integral test to develop a very important test known as the p-test, which is coming up next. Usually, when you're testing some integral for convergence, the integral test, your very last choice. You try everything else that you know first, and if you can't find any other way to do it, then maybe you try the integral test. But for the most part, the integral test is around so that we can use it to develop what we will be calling the p-test very shortly. All right, see you soon.